So let's do some circular motion example problems. One classic example is, let's say you want to go upside down, like in a roller coaster, or you're rolling a marble on a track, or a car on a track, or riding a motorcycle or bike upside down, or flying an airplane upside down. Same thing, and you don't want to fall off, and there's nothing holding you to the track, right? You're just rolling around, there's no bar holding you to the track, and you don't want to fall down because falling down would be bad. So what that means is you want your wheels to be in contact with the track, which means you want to be feeling the track, which means that centripetal acceleration pushing you, keeping you going in a circle, right? You want to go in a straight line, but the track is forcing you to go in a circle. You want to be able to feel that track pushing in on your wheels. So the centripetal acceleration, or the centripetal force, centripetal acceleration is v squared over r, and we want to make sure that that's at least as big as gravity, which is pulling you down, acceleration of gravity, which we know on Earth we're going to round it off to about 10 meters per second squared. So you got to make sure that centripetal acceleration pushing you down, keeping you in a circle, is the same as at least as big as gravity. The other way to look at it, maybe it's more as intuitive, is the centripetal force, that force pushing you down, which is mv squared over r, has to be equal to the force of gravity. So you can still feel it. You want gravity to pull you away. It's got to be at least equal to that, which is mg. The masses cancel. It does not matter how heavy you are. And you get that formula then, just v squared over r equals g, which is 10 meters per second squared, like we said before. So again, it doesn't matter how heavy this thing is. The heavier it is, the more gravity pulls, but the more force you need here, and it mass cancels out. Okay, so that's what you always do. You set the centripetal force equal to whatever force, equal to gravity in this case, going upside down. And you just get this formula. So v squared over r equals g, which, like we said up there, is 10 meters per second squared. So that's real easy math. Let's say the radius of our circle is, make the math easy, let's say 5 meters. So v squared over r is equal to 10. V squared is equal to 10 times r. We said r was 5 meters, so 10 times 5, which is 50. So v is equal to the square root of 50, which is like a little over 7, about 7.1 meters per second. So you would have to go about 7.1 meters per second if you had a radius 5 meters, which is a pretty big thing, right? It's 15 feet radius circle, and you want to go upside down and not fall off the track, just stay in contact. Now I would go a little bit faster than that just to make sure. You don't want to risk it, so maybe go 7.2 or 7.3. Then you'll be really safe, but you could go that fast and not fall off. You'd always be in contact with the track. So pretty easy. That's all you have to do to figure that out. And again, this in miles per hour multiplied by 2.2, around 15 miles per hour. You'd have to go at least 15 miles per hour. Now if you're riding a bike, 15 miles per hour here, you're going to slow down as you go up. So you have to keep pedaling to keep that 15 miles per hour up. So down here, if you're just rolling something, you have to go really fast down here so that as you go upwards, you maintain enough speed so you're still going 15 meters per second at the top. So it's a little bit misleading. That's how fast you got to be going up here, not how fast down here. You probably want to go faster here because you're going to slow down. Okay, that's one classic thing, going upside down, how fast you have to go. Another classic example is having fake gravity in a space station. So let's say you're out in space and you have a big circular station and it looks like a donut or something, and there's something, or you don't have to make it look like a donut, but let's say you do. And then here you are and you're standing in your space station, and let's say the space station has a radius of, let's say you're 6 feet tall, so it looks like about 20 feet, let's say about 10 meters. So the radius is about 10 meters. And let's say you want some fake gravity. In other words, this thing is spinning. Let's make it spin this way, which means it's pushing in on you. There's a centripetal force pushing in on you, and you feel that. You feel the ground pushing on you just like gravity. And there's no way to tell the difference. You'd think at least at that point, you'd think it was gravity because it's pushing in on you, which means you weigh something. If you put a scale there, you would weigh something. Let's say, though, you're in space, you want to at least have a little bit of time off. So let's say you want your acceleration to be, instead of 10, let's say you want your acceleration to be 5 meters per second squared. So you only weigh half as much. So if you weigh 160 pounds on Earth, you only weigh 80 pounds because that's kind of nice to weigh less. So how fast would you have to go in a circle to, or how many circles per second and all those kinds of things to make that work? So we said the radius we just made up was your 10-meter spaceship. How fast are you going to have to make your radius spin so that you can feel an acceleration of 5 meters per second squared? So if you stand on a scale there, you weigh about half as much as you do on Earth. Okay, so typically we want to know what the velocity is. How fast is this thing going to be moving right here? What your tangential velocity is at that point. Okay, so let's see. It's pretty easy. The centripetal acceleration, we have our formula is v squared over r. We want to know v, so v squared is equal to r times acceleration, or just your velocity as the square root of r times your centripetal acceleration that you want. I chose 10 times 5. Oh wow, we get the square root of 50 again. So square root of 10 times 5, which is about, again, 7.1 meters per second. So you're going to have to go about 7.1 meters per second. That's how fast the outside should be turning, so that then you'll feel like you weigh half as much, which again is only 15 miles per hour. That's not crazy. Now, we know that let's just figure out some more things here. So we know that your velocity is also equal to omega r, where omega is the number of radians per second times r. Or omega, then we put the r on the other side as v over r. Well, our v is 7.1 meters per second. Our r was 10 meters. So that's about 0.71 radians per second. So you'd have to go about 0.71 radians per second. That's your angular velocity. So how many seconds for one period then? So the period then, if you want to go a full 2 pi radians, that's one circle, right? 2 pi radians. Divide that by the number of radians per second, 0.71 radians per second. And that would give you the amount of time, because the radians cancel, seconds in the bottom of the bottom is like seconds in the top, so it gives us seconds. That would be how long it would take your spaceship to spin once. So let's see, do that on my calculator. 2 times pi divided by 0.71 is about 8.85, somewhere around that, about 8.85 seconds. So you're going to turn one circle every 8.85 seconds, which means, again, imagine that, going in a circle every 8 seconds, you would definitely get dizzy. They say that if you go greater than or more than once every minute, then 1 revolution per minute, 1 circle per minute, then you will pretty much get dizzy. So to make it so you don't get dizzy after a while, if you actually want to have a spinning space station, you need a much bigger space station. And the best examples are ones like really about a mile across, like a radius of about a mile. Then you can get a reasonable gravity too, something more like Earth, and you would have, and you would not get dizzy, because turning too much in a circle, eventually you'd start feeling it. Now, the other cool things about space stations are, let's think about this. First, his head, this person's head, is not at 10 meters from the circle. It's like, what if it's 6 feet tall? About only 8 meters. So the acceleration at the head, if we plugged in 8 here, we plugged in an 8 instead of 10, it's going to be, well, what I'm trying to say, yeah, if we plugged in an 8 here instead of 10, it's going to be, you'll have less centripetal acceleration, is what I'm trying to say, at your head, if you do the math. So therefore, it's kind of weird. You feel a greater force here than here, and that will also mess you up. Your blood ends up starting, let's see there, your blood would end up going to your feet. which would kind of mess you up there. Or would it go to your head? Let me think about that. Which way would it go? But anyway, you would feel a greater force. You guys can think about that one because I can't think about it right now. You'd feel a greater force your feet than your head, and that difference in forces is also would kind of make you feel kind of woozy and mess you up. Okay, now let's imagine this person wanted to go for a run. So if our person ran in the opposite way the space station was going and happened to run as fast as the space station is going, which is 7.1 meters per second, which is like 15 miles an hour, which is pretty fast, but you could do that. Then you're not moving and you would actually be floating, which means you couldn't run because there'd be no friction, right? You wouldn't be able to push off the ground here. There'd be no friction. So the faster you ran this way, the lighter you would get until when you started running as fast as the space station, you would weigh nothing and you basically couldn't run anymore because you wouldn't get enough friction to push yourself forwards. And then what would happen? And then you'd slow down and you'd start weighing something again. Anyway, it's kind of crazy. So if you run against the motion of the space station, you're going to get lighter and lighter and lighter till you weigh nothing. Now what happens if you run in the same direction? Then you'll be going even faster and faster, and you're going to get heavier and heavier the faster you run. And so you'll feel like, like you weigh a lot more, like more pounding on your feet. So actually running in a space station would be not as straightforward as you'd think if you want to get some exercise running around. This way, you'd be easy exercise, you'd be really light, but if you go too fast, you would weigh nothing, and this way you're going to get really heavy, so it'd be much better exercise, but maybe too good. Anyway, kind of crazy. Hopefully one day we'll have some space stations to try this out on. All right, hope that was helpful. Thanks for listening again.